Hello everyone, welcome to another video on quantum field theory. In this video, we'll be going on a bit of a tangent, and I'll be covering Noether's theorem. Now, you might be wondering, what is Noether's theorem? Well, this theorem is a very important theorem in physics, and it's even more important in the subset of physics, being quantum field theory. A lot of the things that we'll encounter in the future in quantum field theory will use quantities that are motivated by Noether's theorem. So it's very important to get a good understanding of what this theorem is. If you guys don't know what this theorem means, you're in luck, because in this video I'll be covering like 90% of the theorem, and in the next video I'll cover the other 10%. So Noether's theorem, in simple words, just says that a continuous symmetry implies a global conserved quantity. And a symmetry is just a transformation that leaves the Lagrangian unchanged. Now, there might be some words that throw you guys off there, and that's fine. A Lagrangian, if you guys remember, is the functional that gives us the equations of motion of a system once inputted in the Euler-Lagrange equations. So a Lagrangian is represented by some quantity called L, and this quantity L is plugged in to what's called the Euler-Lagrange equations. This is the Euler-Lagrange equation over here in classical mechanics. So you have this mathematical function or functional L that's plugged into this big old equation, and it essentially spits out what's called the equations of motion. And those are the equations that govern how a system will evolve over time. So for example, the equation of motion for a system that's under the gravitational force would be x of t is, I believe, 1/2 gt squared plus vt plus x naught. This is the equation of motion for a particle or object that's under the force of gravity. It tells you where it will be in some moment in time. So the Lagrangian is very crucial in physics, since it helps us determine the formulas that govern how a system evolves. In this case, the system is position. In other cases, like in quantum field theory, our system is the quantum field itself. Same thing in classical field theory, by the way. So the Lagrangian is a very important thing in physics, and I actually gave an introduction to Lagrangian mechanics in my video titled Intro to Lagrangian Mechanics. So I highly recommend that you guys watch that if you don't understand it fully. So yeah, that's the Lagrangian. And a continuous symmetry is a transformation that leaves the Lagrangian unchanged. So say I have some coordinate position x, and I transform x into some new variable x prime, where x prime is defined as x plus some number a. This might change my Lagrangian from L to L prime, right? Since in classical mechanics, our Lagrangian will actually depend on x and x dot. So say we change our system from being in position x to position x prime, that might change our Lagrangian, right? Since our Lagrangian is a function of x, right? And then x dot will change to x dot prime, or x dot is defined as x plus. Well, let's just ignore what x dot is defined as. X dot prime is defined as. So essentially, when we move our system from location x to location x prime, our Lagrangian might change as a result. That's the big idea here. And the transformation from x to x prime, that's called a transformation, right? And a continuous transformation is just a smooth transformation. It means that there's no gaps in the Lagrangian, essentially. And it's defined for all values of x, and we have a smooth transformation. So it's just, there's no holes in our transform. It doesn't matter that much, but that's what a transformation is. a continuous transformation is a smooth transformation. There's no like jumps or anything. There's no discontinuities that we're considering. So this implies a global conserved quantity. Now, what is a global conserved quantity? Well, a global conserved quantity is just some mathematical quantity that does not change over time. For example, you might have learned in like middle school or high school that energy is conserved. Energy is a conserved quantity, meaning that energy, the rate of change of energy over time, will be 0. This means that energy is a conserved quantity. And this equation is called a conservation law. Conserve the environment, right? So that's the big idea. So I spent a lot of time on like that portion. It may seem trivial, but I just want to make sure that you guys like fully understand what I'm saying when I say a continuous symmetry yields a global conservation law. So now that we've got that down, let's advance things a tad bit. So in quantum mechanics, like we say that a continuous symmetry of the Hamiltonian implies a global conserved quantity. So in quantum mechanics, we deal with the Hamiltonian formalism, where we have the Hamiltonian is defined as minus h bar squared over 2m second derivative of x plus r potential. So this is in quantum mechanics. And a continuous symmetry of the Hamiltonian implies that there's a global conserved quantity. And I actually taught this in my video, but why is momentum conserved? So there's also in QFT we deal mostly with Lagrangians. In quantum mechanics we deal with the Hamiltonians. So there's an analogous form of Noether's theorem for Hamiltonians, and I covered that in my "But why is momentum conserved" video. So it's a continuous symmetry of the Hamiltonian implies the operators commute, which implies a global conserved quantity. That's for quantum mechanics. In this video, we will cover the Lagrangian perspective of Noether's theorem, which states that a transformation that leads to the Lagrangian unchanged implies a global conserved quantity. So let's actually dig into it. Alright, so the Lagrangian for a free scalar field is this. It's a function of the quantum field phi of x, partial mu phi of x, and x. And this equals, I believe, 1/2 partial mu phi partial mu phi, and then like plus m squared phi. I don't have the Lagrangian from the top of my head, so this might be a tad bit wrong, but the basic idea is that the Lagrangian for a free scalar field depends on phi, the derivative of phi, and x, and x with an arrow on it. Well, in the 4 position. That's what it's called. I forgot what it's called for a second. So if you guys are not familiar with this, I highly recommend watching my video titled "The Lagrangian Density for a Free Scalar Field." Wait, no. Yeah, I think that's what it was called. So watch that video if this is unfamiliar to you. And by the way, technically speaking, this is not the Lagrangian, but the Lagrangian density, where the Lagrangian density is like defined as the integral of the Lagrangian L. So this is the true Lagrangian. Here's the Lagrangian density, and that's what we use over here. There's a Euler Lagrangian equation for the Lagrangian density as well. So yeah, here's the Lagrangian density. I'll just call the Lagrangian density the Lagrangian for now, because that's just faster. So here's the Lagrangian for a free scalar field, and we can put this into the Euler Lagrange equation and find and solve. Sorry, we can put this into the Euler Lagrange equations, and from there it outputs our equations of motion. That being the Klein-Gordon equation. looks like this. So if we put this into the order Lagrange equation, it spits out the likely Klein-Gordon equation, which we can then solve for the free scalar field. Alright? But that's not what we care about today. We care about conserved quantities. So what do we do now? So say we have a transformation that takes, let's ignore this for now. This, by the way, applies for all Lagrangians in QFT. I was just using the free scalar field Lagrangian as an example. So say we have some transformation where the forward position x turns into x prime, and then phi turns into phi prime, and our Lagrangian or Lagrangian density turns into L prime. And here x prime is defined as x plus delta x, where delta is an infinitesimal translation. Phi prime is defined as phi plus delta phi. And then lastly, L prime is defined as L plus delta L. So this is just saying that we're just moving our system from position x to x prime. We're just like taking this x and removing it by some infinitesimally small number. And since our field phi depends on x, right? We have phi of x. It will also move, or not move, it will also change by some amount, delta. And Lagrangian will also change by some amount, delta L. Alright? So, if we have a continuous symmetry, this means, well, not really if. Okay, let me just reword that. So a continuous symmetry just means that L equals L prime for the transformation of x to x prime. Yeah, so x to x prime, if L equals L prime, we have what we call a continuous symmetry. So if L equals L prime, or L prime was L plus delta L, right? Which equals L plus delta L. This means that delta L is 0. This just makes sense, right? If our Lagrangian doesn't change under that transformation, this means that this delta L term will be 0, since our ending Lagrangian will be the same as our starting Lagrangian. So delta L will be 0. So now what we can do is you can actually, do more. I should have probably worded that better. Alright, so, wait, also one more thing. I forgot one thing. Phi, partial mu of phi, will also transform to partial mu of phi prime. And partial mu of phi prime is going to be defined as partial mu phi plus delta of partial mu phi. Alright? Okay, so now let's actually derive the conserved quantities here. What we've done here was really just qualitative. Let's get to some crunching stuff here. Alright, so Lagrangian is a function of phi of x, partial mu phi of x, and x. And then, so L prime will be a function of phi prime x prime, since this will also be changed. Partial mu of phi prime x prime, and then x prime. Okay? And L prime of phi prime x prime, I'm just write this entire thing out. So this, which is just this, over here, will equal, here, let me just write this, below here. Let me just write this over again. It was on a tilt. So L prime of phi prime x prime partial mu of phi prime x prime and x prime is going to be L phi of x plus delta of L of phi partial phi and x. Okay, so we're just writing what we just wrote over here. Where do we write? Over here in more explicit terms. Because remember, this Lagrange is the function of all of these things. Okay, so now let's actually find out what this is going to actually be, because this is a function of all these things, and it's an infinitesimal function. So we can just use chain rule. Is it chain rule? Yeah, chain rule to expand this over here. Recall that chain rule says that if you have some function that depends on a, b, and c, then what is it? df, the infinitesimal function, will be partial f over partial a times partial a, right? No, I think it's dA plus partial f over partial b dB plus partial f over partial c dc. That's the multiplier chain rule, right? So we do the same thing for this infinitesimal Lagrangian. Infinitesimal L of phi of x partial mu phi of x and x is going to be partial L of partial phi delta phi. Since in this case we have delta phi, because delta phi is the infinitesimal movement of phi, plus partial L over partial mu phi delta of partial mu phi plus partial L over partial x delta x. Okay, so all we're doing here is we're expanding this with multivariable chain rule. Technically speaking, we'd have to use a Taylor series, but since we're dealing with an infinitesimal translation, the Taylor series and the multivariable chain rule are exact. All right. So what now? Yeah. By the way, I didn't use d phi because I'm just using the notation delta instead of d. For some reason, we just use delta instead. And q of t. All right. So this is the delta L, right? So what can we do now? Well, remember that our Euler-Lagrange equation, the Euler-Lagrange equation for q of t is partial mu partial L over partial mu phi minus partial L over partial phi equals 0. That's the Euler-Lagrange equation for in quantum field theory. Again, this is covered in my This is actually covered in the derivation of the Klein-Gordon equation from the Lagrange density video, which is in this Q of T series. So this is the Lagrange equation for quantum field theory, and this of course means that the left hand side equals the right hand side, since because if a minus b is 0, that means that a equals b, right? Okay, so here we have a partial L over partial phi, but that just equals this, right? By the Euler-Lagrange equations. So this means that delta L of I'll just write delta L. I think you guys already know that it's a function of all of these. So delta L is going to be partial mu partial L over partial mu phi delta phi, this entire thing actually, then delta phi plus partial L over partial mu phi delta of partial mu phi plus partial L over partial x delta x. So that's the infinitesimal L. And that's what we've derived it to be. All right? So now we can actually note that these two terms can actually be combined in a pretty smart way. We can actually use, well, actually, not quite yet. We can actually go a bit further. We can go a bit further. And say, we can just move this delta inside of these parentheses now. So we can just move this in front, and we'd have instead partial mu of delta phi. So all we're doing here is we're just moving this delta in front, so we have partial mu of delta phi. Okay. So now we can actually combine. Oh, we forgot the partial L over partial x term. So now we can actually combine these terms together by using the chain rule. Now I want you all to recall, or let's recall, that chain rule basically says that, how do I word this? It says that, like, I'm trying to figure out how to word this with this notation. Never mind. Chain rule basically says that we can, like, compact this into partial mu of partial L over partial mu phi, delta phi plus partial L over partial x delta x. That's what it says. So using chain rule, it actually simplified this equation by a ton, right? So I want to explain why this is chain rule. So how do we evaluate this? So chain rule basically says like d over d lambda, or actually no, we don't need, that's multivariable. I was thinking of multivariable chain rule for some reason. The chain rule actually says that, like, the derivative of, like, say you want to find the derivative with respect to, like, say L of A times B. That's going to be dA over d lambda times B plus dB over d lambda times A. That's chain rule. I was thinking of multivariable chain rule to start for some reason. So if we were to expand this would just be partial mu partial L over partial mu phi times delta phi, and then plus partial L over partial mu phi times partial mu of delta phi, right? But remember, that's the exact same thing as this, right? So this is the same thing. Here, let me just make this a bit more. Yeah. So this is the same thing as this, right? And we found out this is just equal to this. So we can just rewrite it as, so we can just, so this is the same thing, as this. So we can just rewrite this term as this term. So we can just, like, compact this long term over here into this small term over here. Okay. So now what do we do next? Well, now let's remember that if we have a symmetry, it means that our Lagrangian equals L plus delta L, which was, remember, L prime, which means that delta L should be 0. So this entire thing, we can just copy this and paste this, should be 0. All right. So we're almost done. So we pretty much like laid the groundwork for Noether's theorem. Now we can consider some specific translations. So let me just like recap what we've done so far, because this is pretty abstract. This like took me personally like a bit to like kind of wrap my head around. It seems like a big tangent compared to my last 3 videos. So for those that might be lost, or those that want further clarification, let me just explain what we've done so far. He basically just said that if the translation x to x plus delta x leaves the Lagrangian unchanged, so leaves the Lagrangian unchanged, this means delta L equals 0. That's basically what we've just said. We just said if x to x plus delta x leaves the Lagrangian unchanged, this means delta L equals 0. It's that simple. But we've just like kind of like rewrote that English statement into like math jargon, right? And this delta L equals 0 implies that this entire thing is 0. That's it, right? Because like if the Lagrangian is unchanged, this means that L plus delta L equals L, and that delta L equals 0. Okay, that's all we've done so far. So I want to make that really clear for those that might be lost right now. All right, so what do we do now? So now let's consider specific translations. Let's consider x to x prime, where x prime is x plus a. So now we are moving away from the infinitesimal picture. We use the infinitesimal picture to derive this equation, but now we can consider like transformations that aren't infinitesimal. So if x to x prime is this means that our field phi goes to phi prime, where phi prime is going to be minus, a should be a vector, where phi prime is going to be minus partial, this a vector is just another vector, all right, that's all. So it's another 4-vector in Minkowski spacetime. So phi prime will be minus partial of phi over partial x times this a vector. Now you guys might be wondering why this is the case. I guess you could consider this a definition if you want to, but the motivation here is that this like x prime being x plus a actually moves our coordinate system backwards by a. It is a plus, but this, if you like do the math yourself, you're actually moving it's the equivalent of like moving your coordinate system itself like backwards, or moving your function backwards. So if it's moving backwards, then our field will change by negative partial phi over partial x, since it's moving backwards. That's like the motivation for this. Okay. And then our partial mu phi will change to partial mu phi prime, where partial mu phi prime is going to be like the derivative of this, which you guys can figure out, right? It's going to be a bit long to write. Well, no, let's just do it anyways, who cares? So that'll be partial mu of like this. I don't want to write all of that in that small space. All right. Okay, so now we're like literally like almost done. Okay, so all we have to do now is we have to just plug this in. Wait, actually, let me just make sure. Let me look at something real quick. Actually, we don't need this anymore. We don't need partial mu prime anymore, right? Since we've actually compacted that into this thing over here, right? So yeah, we don't actually need partial mu prime anymore. So just like disregard that. Like we still have it, but we don't need to use it anymore. So all we need to do now, I'm just going to erase some things over here to make this thing a bit cleaner, is we just plug these things into this equation that we derived here. So partial mu over partial L over partial mu phi delta. Wait, let me think of something. Yeah, okay. Delta phi. See, we have that. So yeah, so delta phi now will be replaced by x plus, well, not x plus a, sorry. It will be replaced by minus partial phi partial x a vector. So this is going to be replaced by that. So you have minus partial phi over partial x a vector. Okay, so we're just like, again, we're just subbing, let me be more specific. We're subbing this into this and this into this. That's just what we're doing right now. So now we have partial L over partial x times partial x plus a. All right, and this entire thing should be 0. Wait, let me just rewrite that in a bit more compact way. Let's move this over here. So plus partial L over partial x times, and this will be, oh wait, did I do something wrong here? So we have delta x was x plus a. So wait, I'm trying to see if I made a slight error here. Ah, okay, I got it. So you have partial x, we would have delta x, right? You would have delta x, and instead it's x plus a, right? But this would, it's kind of hard to explain, but this would be a instead. This would be plus times a would be 0. Because again, I wrote this incorrectly. Yeah, so this a, it's a that goes to this delta x. I wrote it as x vector goes to delta x, but no, a is the analogous part of delta x, right? So this would be the a vector, and this whole thing equals 0, right? Okay, so again, we're almost done. Well, all we're going to do here is we are going to sort of use some notational tricks here. So these are both vectors. These quantities are both vectors. Now we know that if you want to take the dot product of two vectors, v and w, that's just vi wj times ei dot ej, right? This is, if you guys are unfamiliar with this, I recommend watching my metric tensor transformation video that I made way back, like 2 years ago, 1 year ago, long time ago. I was like 14, I think, when I made that. So quite a bit. It's been a minute since I made that video. But watch that video if you guys are unaware of this equation. So this in special relativity. This is just the Minkowski metric ij. So we can just rewrite this as vi wj nij, or vi wi, but instead we interpret the sum to be v naught w naught minus v1 w1 minus v2 w2, and so on. That's like, this shouldn't be anything new to you guys. So yeah, if you guys are unaware of that, watch my just watch my first video in quantum field theory series. I go over that in the first part. All right, so we can just use a bit of a different notation here. Partial L over partial mu phi. I really hope this video saves. Sometimes when I finish uploading the video, it deletes itself for some reason. I don't know why. So I hope this video, if you guys hear my voice right now, this video thankfully is saved. So you can rewrite this in a bit of a sly notation to make things a bit more simpler for us as minus, or actually we can first move this negative sign to this partial L over here. So you have minus partial L over blah blah blah, and then say this is partial mu phi a, sorry, partial nu phi a nu plus partial mu L a mu equals 0. So again, we're just, it's like, again, remember that like v dot w will be like vi w I guess it should be lowered, or this is just v naught w naught minus v1 w1 minus v2 and so on, because of the Minkowski metric. That's what we're doing here. This dot product is just like comes down to that. And partial mu is being defined as partial over partial x nu, and then like a nu is like defined as like the nth component of the a vector. Again, this shouldn't really be new notation, guys. I covered this notation in my first couple of videos in QFT. So this is just like notation that we're doing here. Nothing very big. So what we can now do is you can factor out this a nu or a mu term. You can factor that out. You can factor that guy out like that. Now you guys may be wondering, whoa, how do we do that? Where did this guy come in? This guy is the Kronecker delta. You guys may know it from linear algebra. I covered this Kronecker delta in like my tensor calculus series. Like, I highly recommend watching my tensor calculus series, because what we're doing right here is basically tensor calculus, right? I mean, it has like 9 videos I think inside of it. So watch that series if any of this like notation stuff seems unfamiliar to you guys. So the Kronecker delta is defined as 1 if mu equals nu, and 0 if mu does not equal to nu. So this means that like when this a mu enters the Kronecker delta, we have partial mu nu a nu L, right? So this will convert the, how do I say this? So let's move this down. This Kronecker delta will like convert this a into a mu L, since it's 1 if mu equals nu, right? And 0 if it's not that. So it changes the a nu into an a mu, and this guy goes to 1, right? So it's really a trick to factor this guy out properly. All right. So what we can do now, we're almost done. I've said that we're almost done for like 3 times now. I'm very sorry, guys. I'll try to speed up, but like I go too fast sometimes. So I tried to slow down a little bit, give a more chill vibe. Anyways, no more jibber jabber. Well, never mind. But okay, so what we can do now is we can say that, yeah, we can just multiply both sides. We multiply both sides by -1. All right. Now we don't really have to do that, but most textbooks do that because of, I don't know, but most textbooks just do that. So we'll do it too for the one guy that's following this from Peskin and Schroeder. So we multiply both sides by -1. This makes this become a minus, and this is just 0 times -1, which is still 0. Anyways, we define this as T mu nu, which is defined as the stress energy tensor that you guys may have seen from general relativity. Yeah, the general relativity version is actually, I think, there's more nuance to it, but like it's kind of like it. So this is stress energy tensor. Oops, sorry, not my pen. The tensor, these are actually the components of the tensor. Since remember that the tensor actually contains the basis of E mu and the covector dual basis combined with the tensor product. If this is unfamiliar to you guys, watch my tensor product video. Yeah, that tensors are pretty cool. They're used a dang ton. Yeah, so these are defined as the components of the stress energy tensor. So it's just a definition here. Nothing too like weird here. So we have partial mu, T mu nu times A nu equals 0. We divide both sides by A to get that partial mu T mu nu equals 0. I want to make this clear. This is a mu, okay? Yeah, and this equals 0. So these are the same thing. So these are the same thing, and this is a different thing. I know that mu's and nu's look the same. If I were like, well, I am in control, but like most textbooks use mu and nu. I don't know why. I think it's the most stupid thing in all of physics. Why would you use both mu and nu in the same line? But most textbooks just do that, so I'll do it as well. I hate conforming to authority, but again, for like the one guy falling from Peskin and Schroeder, it's partial mu T mu nu equals 0. So, yeah, this is a continuity equation. My pen just died right now, sorry. Let's just wait awkwardly for like 5 seconds. 1, 2, 3, 4, 5. So this is a continuity equation. Continuity equation. And continuity equations, like, they kind of allude, they kind of tell you that there's something being conserved. We can actually choose the case for mu, where mu equals 0, and we have partial mu T mu naught equals 0, which we can expand as partial naught minus partial I Ti naught equals 0, where I goes to 3. And recall that partial naught is defined as partial over partial x naught, which is defined as partial over partial t. So this is just partial t naught minus partial I naught equals 0. And this actually tells us very subtly that energy is being conserved, because this term relates to energy. Well, not energy, the Hamiltonian, I should say, is being conserved. We haven't actually shown that explicitly yet, but continuity equations like kind of tell us that something like, hey, something here is being conserved. And we can actually do some math jargon to this term to actually show that energy, which would be like, or the Hamiltonian really, which is being defined as like the partial, it's defined as this, I think. We can show that this is a conserved quantity, that partial t of h will be 0. We haven't done that yet, right? So we will actually show that in the next video. As for now, we will wait in a very eerie moment for the next video. So yeah, I hope you guys enjoyed this. Oh, by the way, I haven't recorded a video in a while because I have school and stuff. I have to study for my SATs, and yeah, I'm pretty busy at the moment. I want to like upload like just like one video, at least one, like before the end of the year, to like keep you guys like, like having more videos to watch and stuff. I have quite a lot already, but like I just want to like make like one more video, at least one more, before the end of the year. So I'm not posting very frequently right now. This actually might be the last video of this entire year because I'm pretty busy, but I just want to take this moment to say like thank you to all of you guys. I read all the comments. I really appreciate all the feedback. Without you guys, this channel would be like less popular, right? I'm almost at 100 subscribers. I really value all of you guys' input. I take notice of them. I've tried to write more clear. I've tried to talk slowly, though I might have failed at the latter. But yeah, thank you guys for all your feedback, and yeah, this has been an awesome year, awesome COVID year. This might be the last video of 2021. So yeah, see you guys later. Stay curious. Bye.